in task 1 we saw given arbitrary motions at the joints q1, q2 and q1 dot and q2 dot, we figured out how to calculate x, y end effector coordinates and end effector velocity components x dot and y dot. Now in task 2 we need the exact opposite of this, right? So given end effector positions, we want to find out what the motors need to do, what q1 and q2 should be. So task 2 need inverse calculation of task 1. So task 1 we said has a name, it's called forward kinematics. So this, then you might have guessed, obviously has inverse kinematics as the name, because you are now doing the inverse calculation. Now what you can do is use the same two equations, equations 1 and 2, and solve them numerically to find q1 and q2 given x and y. So let me say there are 3 ways to do this. So first one is solve 1 and 2 numerically, and that is not very convenient in many situations. Remember, for a typical robot task you need to be able to do this at every time step. While the robot is moving, at every instant you need to be able to calculate what the next step q1 and q2 should be, or what the motor should be doing in the next time instant. So anything that is numerically computationally intensive, which can take time to compute, is not a very elegant solution, especially when you are dealing with relatively long trigonometric relationships. Now remember, if you had multiple links here, you would have those equations have several sines and cosines. So you can do this, but not the best way. The other way is if you had a closed form solution. What is a closed form solution? It means you have an equation for q1 and q2 explicitly in terms of x, y, x dot, y dot, without you having to do any further integration, differentiation or any other solving. This would be of course the most convenient, but in the general case this is difficult. This is not always feasible, but fortunately for us, for 2-hour manipulator, this is something that we can easily do, and we will do that in a second. There is a third approach, which is again a numerical approach, but a slightly different numerical approach as compared to what I mentioned in one. And this, it turns out, is the most commonly used approach today in industry, and we will talk about this sometime later on. But for a 2-hour manipulator, let's see if we can work out a closed form solution. So to work out a closed form solution, we will need to do some trigonometry. So let me draw a couple of triangles there and then do, apply some trigonometric identities to figure out expressions for q1 and q2. So first triangle, let me draw the same two links. So this is L1, L2, and this coordinate is xy if this is the origin, right? And now let me complete this triangle. This is now an obtuse angle triangle. The length of the blue hypotenuse is nothing but, using the distance formula, square root of x squared plus y squared, right? So if I want the square of the hypotenuse, I'll get x squared plus y squared. Okay, let me also define a new angle here, theta, and theta is nothing but second joint angle, but measured in a relative sense, relative to the first link, right? So we just talked about the fact that here we have defined it q2 as an absolute angle, and it is not very natural. We would in many cases want to switch to a relative angle. For the moment, let me still keep q2 as the absolute angle and then just define this angle theta. So this is one triangle. Now here we can calculate theta using cosine rule. I'm sure all of you have forgotten what is cosine rule. It's nothing but Pythagoras theorem, but applied to triangles that don't necessarily have a right angle in them. So in this case, this is an obtuse angle triangle. So if you remember, cosine rule is nothing but hypotenuse square is equal to first length squared plus second length squared minus 2 times length 1 into length 2 into cosine of the angle between them. So in this case, the angle between them, which is the obtuse angle, is 180 degrees minus theta. So I can switch to theta and get a negative cosine theta. So cosine of 180 minus theta is negative cosine theta. And from that, I can calculate theta. So here I would get theta is equal to cosine inverse. Hypotenuse squared is just x squared plus y squared, as I just talked about, minus L1 squared minus L2 squared divided by 2 L1 L2. Okay, so this is my first expression for theta. Now I need to draw another set of triangles to be able to go from theta to Q1 and Q2. So for that, let me redo the same thing, but now so this is still xy. Now let me complete the red triangle here, where again the hypotenuse of the red triangle is x squared plus y squared, the square of the hypotenuse, but the vertical over here is just y and the horizontal is x. And let me also draw a blue triangle which is extending this first link until you hit a perpendicular from the end effector. So I hope you can see, we will first look at red triangle, then blue triangle, and use the red triangle to calculate this angle beta, and use the blue triangle to calculate this angle gamma. And as you would have guessed already, your Q1 over here is nothing but beta minus gamma, right? So this is now relatively straightforward triangle identity. So beta is tan inverse of y over x, and gamma is tan inverse of opposite over adjacent. Opposite is L2 sine Q2. So tan inverse of L2 sine Q2 divided by, or rather sine theta divided by adjacent is L1 plus L2 cosine theta. So L1 plus L2 cosine theta. So this gives me Q1, and when I know theta and when I know Q1, then my Q2 is straightforward. It is simply Q1 plus theta. So these two equations give me a closed form expression for Q2 and Q1 when I know x and y. So this is task 2. As I said, when you have many more links and when you have three-dimensional geometry, this is not always feasible, and we will have to resort to 1 or 3, and we will talk about those later. But for the time being, we are satisfied with this, and this gives you an idea of inverse kinematics for 2R or planar elbow manipulator.